Dear learners, I welcome to this video lecture number 4 in Unit 2 Metrology of the subject Air Pollution and Control Engineering. In this video, we are going to see stack plums and its characteristics. The general characteristics of stack plums is dispersion of pollutants, carries pollutants downstream from source, causes pollutants to flocculate from mainstream in vertical and crosswind direction. This is called as atmospheric turbulence. Mechanical and atmospheric heating both present at the same time but in varying ratios in the plums affect plums dispersion differently. 6 classes of plum behavior. First, looping. Pollutions that is released into an unstable atmosphere which forms looping plumes. Rapid changes in temperature and pressures may result in plumes that appear billowing and puffy, which cause high degree of convective turbulences and form superadiabatic lapse rate. While unstable conditions are usually favorable for pollutant which has high concentration of air pollution forced down by cooling air can be harmful if trapped at the ground. Associated with clear daytime conditions and accompanied by strong solar heating and lighting winds. This looping plumes occurs on sunny days with light to moderate winds which combine with the rising and sinking air to cause the stack gases to move up and down in a wavy pattern which producing a looping plume. So the figure shows the plume with a waving pattern and the graph which is drawn between temperature and the elevation. The x-axis represents temperature and the y-axis represents elevation. The dotted lines shows adiabatic lapse rate in the graph and the straight line shows environmental lapse rate. Then coning. Neutral or slightly unstable conditions create a cloning plume that is distinguished by large puffs of pollutants, which is occurs in neutral conditions, which is stable with a small scale turbulence. Associated with overcast, moderate to strong winds, which forms roughly a 10-degree cone. Coning plumes are typically formed on partly cloudy days when there is an alternate warming and cooling of atmosphere occurs. Warm gases released into cool ambient air and expand and rise into the upper atmosphere, which forms coning plumes. The pollutants travel fairly long distance before reaching ground level. The figure shows the stack with the coning plumes. The graph represents the adiabatic lapse rate and the environmental lapse rate, which is the difference between temperature and elevation. The x-axis represents temperature and the y-axis represents elevation. Fanning plumes. A fanning plume occurs during stable conditions and is categorized by long flat streams of pollutant emission. Occurs under large negative lapse rate. Because atmospheric pressure is stable, there is neither a tendency for emissions to rise or descent, permitting wind velocity to transport and disperse the pollutants. The strong inversion at a considerable distance above the stack will occur, which is extremely stable atmosphere condition. These plumes having little turbulences. If plume density is similar to air, travels downward at approximately same elevation. Fanning plumes are usually seen during the early morning hours just before the sunshine begins. Then fumigating plumes. In the early morning, if the plume is released just below the inversion layer, a various serious air pollutions could develop. The stable layer of air lies a short distance above release point with unstable air beneath. When pollutants are released below the inversion layer, gaseous emissions quickly cool and sent to the ground level. This condition is known as fumigation and results in a high concentration of pollutants that can damage to both humans and the environment. Significant ground level concentrations may be reached. Lofting is the opposite condition of fumigation. When the atmosphere is relatively stable, warm air remains above cool air and creates an inversion layer. Inversion layer below with unstable layer. Pollutants are dispersed downwind without significant ground level concentration. Pollutants released below the inversion layer will remain trapped at ground level, and in the absence of any atmosphere instability prevents the upward transportation of pollutant. The figure shows the lofting plume which is coming out from a stack. When there is little or non-vertical mixing, pollutants tends to form high concentrations at ground level. Trapping. The inversion above and below the stack causes trapping. Diffusion of pollutants is limited to different layers of inversion. This figure shows different stacks and pluming behavior of the stack and the graphical representation between environmental lapse rate to the adiabatic lapse rate. Effective stack height. The effective stack height is the height above ground level at which the plume begins to travel downwind. The effective release point of the pollutant and the origin of its dispersion. A number of empirical models exist for calculating the plume rise h. which is the height above the stack to which the plume rises before dispersing downwind. Three equations that give a reasonable accurate estimate of plume rise have been developed by Carson and Moses in the year of 1969 for different stability conditions. For super adiabatic condition, the formula is shown, which is delta H is equal to 3.4 times of Vs, which is nothing but stack gas exit speed d stack diameter divided by u plus 5.15 times of QH, which is heat emission rate from stacks, power 0.5 divided by U. For neutral condition, delta H is equal to 0.35 times of stack gas exit speed into stack diameter divided by U plus 2.64 times of heat emission rate from the stack, power 0.5 divided by U. For sub-adiabatic conditions, the formula is shown. The parameters are same. This is an example to determine the stack height. A power plant has a stack with a diameter of 2 meter and emits gas with a stack exist velocity of 15 meter per second and a heat emission rate of 4800 kilojoules per second. The wind speed is 5 meter per second. Stability condition is neutral here. This want that estimate the plume rise. They asked the plume rise. And also the effective stack height also they asked. They give the geometric height of stack is 40 meter. So we apply the formula of delta H, which is suitable for neutral condition, which is nothing but 0.3 times of Vs, which is called as speed of exit gas, into diameter of stack divided by wind speed plus 2.64 times of QH divided by wind speed, which gives 38.7 meters. Hg is nothing but the geometric height, and the H, which is determined by using the formula for neutral stability conditions. The addition of both gives the effective stack height.